So we had quite a few tools to analyze discrete time Markov chains, and what we're going to do now is see that most of them transfer over to continuous time with little, if no, modification. Here are the concepts from discrete time chain analysis: reversibility, irreducibility, periodicity, recurrence, limit theorems, which had to do with how transition probability of a chain approached its stationary distribution, and first step transition analysis, which had to do with computing the expected value of a Markov chain at some point in time in the future. Kind of looking down the list, all of these will translate over with a very minor, if any, modifications to continuous time, except for the notion of periodicity, which actually makes no sense whatsoever in the continuous time setting. Periodicity in discrete time had to do with a state being revisited in multiples of a certain time unit. There's no natural time unit in continuous time, and so there's no periodicity. There's no such thing as a greatest common divisor, which was needed in discrete time to define this notion. And so this thing is essentially gone. I'm going to cross it out, and what we're going to do is now move down this list, and I'll let you know kind of which modifications are needed for each one of these concepts to translate over. First on the list is reversibility, and this one is super simple. You need local balance conditions. You need to verify them in order to conclude that a discrete time Markov chain is reversible, and so there's a natural analog of this, as we've already seen. These are the reversibility conditions for a continuous time chain X, and you see what happened. All we've done is we've replaced the one-step transition probability by the generator. And so, in either case, it's just a matter of, for all pairs of states, verifying these local balance conditions and concluding that the chain is reversible if the statement holds, and not reversible otherwise. There was a concept of a time reverse chain, which also has its own analog in continuous time, except in discrete time we defined the one-step transition probability of the time reverse chain. Here we're going to define the generator of the time reverse chain, and when the generator of the time reverse chain matches the generator of the original chain is reversible. So all these concepts translate over. And as you can see, the generator plays the role of a one-step transition probability for the continuous time chain. Irreducibility, this was a very simple notion in discrete time. For all pairs of states, you had to find a finite time such that you can go from that state to the other in that time with positive probability. So there it is. In the continuous time, this is going to take a little bit of thinking. I'll let you kind of think through this. But the statement is that if you can verify this for the embedded chain, which has probabilities bxy, then the continuous time chain will be irreducible as well. So this is the statement: a continuous time chain is irreducible if the embedded chain is irreducible. And I mean, its embedded chain, right? So not any embedded chain, but its embedded chain has to be irreducible. And this really, kind of as you think through this, you have to kind of consider this notion a little bit, the fact that there is a certain convention that these embedded chains satisfy, and that goes into establishing this fact here. We have this theorem in discrete time, which now I'm going to restate in continuous time. It's virtually identical. So if a continuous time chain is irreducible, then all states fall into one of the following categories. They're either all transient or all recurrent, and within the recurrent branch, they're all going to be either all positive recurrent or all null recurrent. So now all we need is some definitions for what this all means. Here is the case of recurrence. So this is a review of the definition from discrete time. Start out in state X. Define a return time to state X. This is the number of steps until we're in state X again. And if this is finite, if you took a finite number with probability 1, then the state is recurrent. In continuous time, same exact thing with one little change. We still start out in state X. We still look at the return time, and this return time better be finite. But the way we define it is that it has to be greater than the waiting time in that original state for obvious reasons. you have to leave the state before you can start counting how long it took to return. So if you look at the diagram below me, we start in state x, and that first step is that length tau x. We're going to have to wait for that to elapse before we start counting that the chain returns. So the return time has to be greater than tau x, and we look for that first time since it leaves state x for its return. This is no wrong. It's just return time is finite, not mean return time. So return time is finite with probability 1, just like up there. It's a mistake right there. Okay. So now one little convention on absorbing states. We're going to define the return time to be 0 if we wait in that state forever. So this is a little bit of a matter of interpretation or convention, but basically it says that absorbing states, those with 0 rate, meaning that you stay in them forever, are recurrent. So that's just a matter of convention that's assumed pretty much everywhere. And now what we can actually notice is that the definition of a recurrent state boils down to checking the same for the embedded chain. So this is a little bit surprising maybe, and it's similar to the same fact for irreducibility. So in the case of irreducibility, we had the same thing. The embedded chain determined whether the continuous time chain was irreducible. The same thing happens here. If the embedded chain starts at state x, so x0 is the same thing as z0, the starting location of the embedded chain z. So if we start at x and the embedded chain takes a finite number of steps, then the state x is recurrent for the continuous time chain. And the reason is because of this definition. The actual continuous return time is just the sum over the number of steps that it took for the embedded chain to return, and you're summing up a bunch of finite things. So you can think about why I say these are finite, or think about a contradiction when it's not finite. When it's not, then the actual embedded chain is not recurrent. So when the embedded chain is recurrent, you're going to have all of these things be finite, and you're going to have k be finite, and therefore the total continuous return time is also finite. So in other words, the summary here is that there's sort of parallel definitions for recurrence of a state, and the recurrence of a state in continuous time can be determined solely on the basis of the embedded chain. And then finally, if a state is not recurrent, it's transient. So that's just by the definition of what it means to be not recurrent. Okay, for positive recurrence, we're going to look at the same return times and the same starting state x, and we're now going to have to look at not the finiteness of the return time as a rate of variable, but its finiteness in expectation. So both of these have to be verified, and it may be a little bit tedious. You can see how this definition now works well. The return time is 0 if we stay in that state forever. So absorbing states have a 0 return time, and that means that also an absorbing state is positive recurrent. And then further, if we have a recurrent x and it turns out to be not positive recurrent, then it's called null recurrent. So if this evaluates to infinity, not up here. If this evaluates to infinity, then the state is null recurrent. And of course, that's true in both cases. So it's actually true in the discrete time chain setting as well. Word of caution. So we saw that the embedded chain can determine irreducibility and it can determine recurrence. It cannot determine positive recurrence. And here is a calculation to show this. So if we are going to take k as the number of steps for the embedded chain to return to the state x, we can write down the actual continuous return time as the sum over k waiting times. Now you can use the Tower property to condition on the embedded chain, take the expectation in, and compute that expectation. This is the expected waiting time in state given by zk minus 1. So wherever the chain is at time k minus 1, whatever the embedded chain is, that's what we compute the waiting time of, and that's equal to 1 over r and the state that's given to us by the embedded chain. And so what you see from this calculation is that the rates of the states make a difference in computing the mean return time. And so in other words, the embedded chain is not enough to determine whether a state is positive recurrent or not in the continuous time setting, whereas for recurrence, it is actually sufficient. Here's a theorem that we had in discrete time, paraphrased for continuous time. If we have an irreducible continuous time Markov chain with at least one positive recurrent state, then X itself is positive recurrent, meaning that every single state is positive recurrent, and it has a unique stationary distribution given by this equation here. You may remember that in discrete time, this R was just not there, and this T was replaced by the number of steps that it took to return to the starting state X. In terms of limit theorems, again, things are fairly one-to-one. So here's the main limit theorem for discrete time chains. If the chain is irreducible, aperiodic, and positive recurrent, then there is a unique stationary distribution, and the transition probabilities of the chain approach that stationary distribution. That was the main limit theorem in discrete time. In continuous time, the word aperiodic, this one, is not going to mean anything, so it's dropped. But there is something that's added, which is non-explosive. So we need X to be non-explosive. I'll talk about what this means in a second. The other conditions stay the same. Irreducibility and positive recurrence stay the same, and you have a long-run transition probabilities converge to the stationary distribution pi. And what does it mean for the chain to be non-explosive? Well, let's look at what it means to be explosive. So if you look at the picture below me, you'll see the jump times of the continuous time chain. So T0, T1, T2, T3, T4, so on. These are times at which the CTMC changes state, or jump times. And these can either kind of run out to infinity, which is the case of non-explosiveness, or suppose for a second that I design my rates in such a way that every single successive intervals is sort of on average going to get shorter and shorter and shorter, and so the time between T2 and T3 is longer than between T3 and T4, and then the time between T4 and T5 is even shorter, time between T5 and T6 is even shorter than that, and so on and so forth. And so they will kind of maybe shrink, one has to design this chain, of course, but they could shrink so rapidly so that these jump times will actually approach some finite, random variable or even some finite time. And this is called the point of explosion. And so, in other words, just run up against this finite time, and the chain sort of exhausts all of its switches of state before then. And that is something that you cannot allow for obvious reasons, in that here we're taking the limit as t goes to infinity. And so you need something not explosive, which is just a statement of the fact that these jump times, tk, go out to infinity, which is the more natural sort of way to specify a chain. And I wrote down a quick little condition here for non-explosiveness. If this infinite series diverges, goes to infinity with probability 1, then the chain is non-explosive. So, for example, if you have rates that are bounded, so suppose the rates R are bounded above by some number, then they cannot become large enough, and the sum, regardless of z, will explode. And so, for example, a chain with bounded rates will always be non-explosive, and then you can apply this limit theorem. Oh, okay, so we're at the end of this clip. In the next clip here, called the astronaut's oxygen problem, I'm going to show you an example of first step transition analysis.